Click the bell icon to get latest videos from Ekeeda.
Hello friends, I welcome you all to this video. We are with chapter 6 of microwave engineering. So far, after the bipolar junction transistor for microwave applications, then the heterojunction bipolar transistor, then the junction field effect transistor, we are now covered with the metal semiconductor field effect transistor. Now let us address the cutoff frequency and the maximum oscillation frequencies associated with this device. So here we start with our topic where we require the knowledge of cutoff and that of the maximum oscillation frequencies if we operate the MESFETs here. So when we account for the generalized expression for the cutoff frequency, that is denoted by F suffix CO for the wideband lumped circuitry, we get it into the form of G suffix M, the transconductance, divided by twice pi into C suffix GS. It is the capacitance between the gate and the source terminal here, which can also be expressed in terms of V suffix S divided by 4 pi L. So as this is the frequency, it must be accounted in terms of hertz here. So here we express the parameters on which the cutoff frequency is dependent on. So Gm is the transconductance. CGS that we have shown that it is nothing but the gate to source capacitance. This capacitance can also be expressed in terms of differential of the charge with respect to the differential of the potential applied VGS, provided the drain voltage is equal to a constant value. The representation of the capital L is nothing but the gate length, and the representation of V suffix S is the saturation level of the drift velocity. I only mention saturation drift velocity. Now when we talk about the maximum oscillation frequency, the maximum oscillation frequency can be denoted by F max here, and it is dependent onto the transconductance value of the device, as well as we require the drain resistance into consideration. So it is simply the cutoff frequency FCO divided by 2 in multiplication 2. Here we have Gm into the drain resistance RD in the square root here. So we express it in the terms of FCO divided by 2. The square bracket involves mu into capital E suffix rho in multiplication to mu suffix M minus rho divided by V suffix S in the bracket 1 minus mu suffix M here. So the square bracket is under square root, and here we have the frequency of maximum value for oscillation accounted in terms of hertz only, where we express the various factors involved. R suffix D is nothing but the drain resistance. G suffix M is the device transconductance. E suffix rho, here we have, that is the electric field, and this is at the pinch off condition here. So we must call it to be the E suffix P here. We have mu suffix M is equal to the saturation normalization of U here. And finally we have V suffix S, mu and rho that have been the saturation drift velocity, and these two parameters also we have addressed previously here. Now when we take the condition that rho is equal to 0, that means gate to source voltage we have kept to be equal to 0, and the eta parameter defined earlier that it is very greater than 1. So far the cutoff frequency f suffix co is equal to the saturation velocity Vs divided by 4 pi L, and also mu suffix m is equal to 3 divided by eta, that has the power 1/3, which will be very less than 1. So in this situation the maximum oscillating frequency f max we obtained as gamma in multiplication to v suffix s divided by L in the bracket 3 divided by eta, that has the power 1 divided by 6, accounted in terms of hertz here. So here gamma we obtained 0.14, and this is for mu into EP divided by Vs is equal to 13. Gamma is equal to, we go for 0.18 for mu into EP divided by Vs is equal to 20 in the case of the material gallium arsenide here. When we have the gate length for the gallium arsenide material used for the MESFET having the gate length L less than the value of 10 micrometer, so this implies to the value of maximum oscillating frequency f max given as 33 into 10 raised to power 3 divided by the L in terms of hertz here, where L is the gate length. So in the SI system of units it is measured in terms of meters. The best value of L to obtain the maximum oscillating frequency is 0.5 micrometers here. So whatever the maximum oscillation frequency we have discussed so far, it is similar to that of the cutoff frequency that has been determined by the transit time that we generally denote by the letter tau here. So here the cutoff frequency FCO is equal to 1 upon 2 pi tau here, or we can also express it as Vs divided by 2 pi into capital L. So this is in terms of hertz, because tau is the time, so the time taken by the charge carrier to travel this much of length that we have accounted in terms of the velocity and the length here. So tau will be simply L divided by Vs. L already we have mentioned it is the gate length, and Vs is the saturation drift velocity in terms of meters per second we can say. Finally, the high frequency of oscillation for the maximum power gain with the input and output networks, those have been matched, can be given as f suffix max is equal to the cutoff frequency FCO divided by 2. In the bracket here we have RD listed as before, divided by the addition of RS with RG with that of the RI here. So those have been in the square root. So this is into the hertz here. This will be the very helpful formula for determination of maximum oscillating frequency here. So the meanings of the RD and rest of the resistances I mention again. This is the drain resistance, whereas RS is equal to the source resistance. RG is equal to gate metallization resistance, and Ri is equal to input resistance. So here we complete our topic, the cutoff and the maximum oscillating frequencies with respect to the device under consideration, that it is metal to semiconductor field effect transistor. In the next lecture we shall be using this formulae to solve a simple problem. I hope you are definitely enjoying the subject. For more information and the details of microwave engineering topics, you can subscribe to Ekeeda channel. Thank you.